you, Mr. President, for giving me this very great honour. I'd like to thank the members of the University of Rennes community in general as well. Thank you, Professor Monjan and Dr. Paul, for the very kind introduction to my background and our collaborative research. And thanks, Fred, for the very quick introduction to nonlinear optics, which will make this presentation maybe easier to follow for the audience. So, our focus for a long time now has been on finding ways of transforming light and also finding ways to use it in a useful fashion. What I've shown on the opening slide here are several examples, thank you, of cover images from journal articles that illustrate some aspects of this idea of making use of light in a practical way. So on the left-hand side here, this is an image of the Parliament House actually in Canberra. We are the site of the national capital, and we have Parliament there as well. There's a shape of a molecule that's sort of superimposed on part of this. It sits inside a hill, but what we're illustrating here is the changing of the frequency of light that one can achieve by making use of nonlinear optical materials. In the central image here, we have some images of dendrimers, molecular trees. We work with various types of molecules, different types of compositions. So this is just to illustrate the branch sort of shape that some of them can have. But also the fact that using these types of properties, you can increase the density of information rather than, for example, writing onto a disk in 2 dimensions. On one disk, you can actually work in 3 dimensions. You can work through the interior, and so the information density can go up by many orders of magnitude. This obviously has practical advantages. Over on the right-hand side here, we have an illustration of a phenomenon called optical limiting. The idea here is that you can let light through at low intensity, which is obviously very important to see what's happening, see where you're going. But if you are attacked by intense light sources, such as from laser weapons, you need to be able to block that hostile attack, and you can do this sort of thing using optical limiting materials. Okay, so some of this Fred has already explained, and so what I've got here are a few images that further develop that idea that you've just seen on the previous slide. So we've seen examples of making use of optical fibres. We also saw an example of moving the data storage to 3 dimensions and increasing the information density. These sorts of effects rely, in many cases, on intense light that one only finds at the focal point of a laser beam, and this means that if you focus down into a material, you can do things within those 3 dimensions. And so apart from 3-dimensional data storage, you can also microfabricate. So you can use this to build things at very small scales. Similarly, from the 3-dimensional point of view, you can use these materials for medical imaging. You can also use it in 3 dimensions to deliver therapy as well. So this capacity to be able to operate in 3 dimensions can be very, very useful. And we have also already seen the idea of protection of sensitive optical devices such as your eyes. So Fred has said a little bit about the background to this area, but without going into too many details, we understand the processes by which these nonlinear optical properties arise, and what we're trying to do is to magnify and enhance the magnitude of these key coefficients that are responsible for the nonlinear optical effects. So on the next few slides, you'll see some examples of maximising these sigma n coefficients, and beta is the other target. So when we got into the area, most of the previous work had been with inorganic crystals and with organic materials, and I am by background training an organometallic chemist. This was a PhD with Michael Bruce. Organometallics had been exploited in other areas at this time, and you can see examples on this slide here of the impact that organometallics will have had on your everyday life. So even if you may not have come across the terminology of organometallic before, you have for sure made use of products that exploit organometallics in their synthesis. And there's examples from different areas of modern life that for sure you will have been exposed to. So, roughly contemporary with when I started my independent research career, a publication came out that highlighted the possibility of organometallics in this field, and this was a key driving force of encouraging our activity in the area. This report, which is in Nature, obviously a very prestigious journal, made use of so-called Metallocene compounds, and without going into details of the chemistry, because I know that a lot of the audience are not chemists, it should be clear looking at this diagram here that we've got one part of the molecule that's sort of at right angles to the rest of the molecule, and we want the parts of the molecule to talk to each other. We need to be able to move electrons around through the molecule, and that's easy to do with certain types of molecules where all of the elements are within the one plane. So we've moved from this sort of report, which was in Nature back in 1987, to basing all of our work really on this type of composition where there's a metal and some sort of system that facilitates delocalization of electron density. And we've used this to try and find ways of enhancing these key coefficients. We've got a couple of slides just to show you what these molecules look like. Again, I know that most people here are not chemists, but you might, I guess, find the symmetry of some of these sorts of molecules pleasing. This is a so-called dendrimer or molecular tree, and we build these with variations in the composition, in what's on the outside, in what's in the middle of them. This involves a lot of chemical synthesis, and this is where a lot of our co-tutel and other students that we've shared between our laboratories, this is where they devote a lot of their activity, is chemical synthesis. The idea in moving to these higher coefficients, and this is the focus of our current activity, there are a lot of benefits associated with this. So on the second slide, we saw a lot of examples where you can operate effectively in 3 dimensions at the focal point of a laser, but that spatial discrimination becomes better as you move from sigma 2 to sigma 3, sigma 4. I don't want to go into the details here, but there are definitely some key benefits in that progression. And so over the last 10 years, we've been focusing more on these higher terms. Without worrying too much about the other benefits here, I should point out that a driving force for people in this field is to generate materials that are going to be useful, and there are certain wavelength regions where this utility is enhanced. So tissue has maximum transparency around 800 nanometers. This is the biological window. And silica, which we've seen earlier with optical fibers, has maximum transparency around 1300 to 1550 nanometers. So there are regions of the spectrum where we might find materials to be more commercially valuable, and so we've focused activity on trying to identify materials at those wavelengths. Here's another example of one of these molecular trees, and what we've done here is to move from a purely organic molecule, which is has no metals present, to introducing ruthenium, which is a transition metal. So firstly, we put ruthenium at these sites, and then secondly, we put ruthenium at all of the sites. So we've moved from a non-metal molecule to one with 3 metals and then one with 9. And this is what happens in terms of the properties. Without the metals present, there's sigma 2, 2-photon absorption. You insert 3 metals, we increase this dramatically, and we introduce sigma 3, 3-photon absorption, and you introduce metals on the periphery as well, and we increase the 2 and the 3-photon absorption and turn on 4-photon absorption. And what this is doing is giving us activity at some of the wavelengths that are commercially important. Finally, I just want to say something quickly about switching these properties. So apart from increasing the size of the coefficients, which is going to be commercially important, another thing that you might try and do is to exercise control over these phenomena and to turn them on and off, or to change the way that they're modifying light. And you can do this through so-called molecular switches. So everyone's familiar with turning a light switch on and off, and if you have several lamps or lights together, then the number of possible states on whether lights are on and off goes up by 2 as you introduce each additional light switch. Your readout in this case is the light on, and you can immediately see what the switching state that you've got is. In the case of molecules, instead of using sort of a finger flick to turn on a light switch, we use the presence of certain chemicals or voltage or light, and this in turn could be useful because that, for example, could be used as sensor applications to, for example, indicate the acidity or whatever voltage is being applied. So we're going to use these to change these particular coefficients, and there are possible applications outside of sensors in logic gates. This is the most complicated chemistry slide, and I'm not going to take people through it, but the student who did this work, and she spent firstly some time in Rennes as an exchange student, then she came back here as a postdoc, synthesised this molecule in the lab, and what you can do is to take electrons away from that molecule to generate that form. You can add acid to the molecule to make this form. You can shine a light on it and change the structure. You can see that this unit here is changing without worrying too much about what the specific is. But all of these different states of the molecule can then be accessed with these stimuli. They afford species that all have different nonlinear optical properties. So this is functioning as a multi-state nonlinear optical switch that can be accessed through all these different pathways. So this is a goal at the moment of our nonlinear optical work in conjunction with the University of Rennes, is to make new types of molecules that can function across a multitude of states. So the connection between the ANU and Rennes has involved improving the values of the coefficients that Fred has introduced and that I've further explained here, and to expand the number of switching possibilities that we have access to. Now, one of these areas of collaboration has involved making use of porphyrins, and this has involved a connection with Christine Paul and Fred Paul. What we've done is to make some of the molecules at the University of Rennes. Other components have been previously prepared at the Australian National University. These can be clipped together to make large species, as you see here. This is actually it has the same structure as something from medieval heraldry, a cross-fourche. So you can actually find an example of that in a Templar church in the UK. Probably just to highlight it, because it's tended to fade over time. You can see that this has got roughly the same sort of structure here. When we're chemists, we have complete flexibility over building things, so if you're inspired by some sort of design somewhere, you can just go away and make that type of molecule. And it turns out that this has an extraordinarily large value of one of those key coefficients that I mentioned. Final point is that the Rennes group that we've been collaborating with for an extended period of time are experts with iron. I didn't say too much about ruthenium, but it sits in the periodic table of the elements just below iron, and so they have some sort of similar properties, but they have some differences as well. And the iron is easier to take an electron away from than ruthenium. So if you make these sorts of heterobimetallics, which has been done as a collaboration between Rennes and the ANU, you can increase the application of a potential, take an electron away from the iron to generate the blue compound here, take another electron away to generate the green compound. Each of these three forms, which are colour-coded, have got different linear properties, and you can use this to switch the nonlinear optical properties as well. We've taken this a step further by attaching this to hydrogenated silicon surface to make supported nanostructures. Okay, so from that very brief summary of some of the things that we've been doing, and I guess emphasising the research that's been done collaboratively with the University of Rennes, I wanted you to take home the message that these sorts of species are very efficient NLO materials. We have world record values of the key coefficients. So these coefficients are what are being used to manipulate and modify light, and we can make molecules that have the largest values of the coefficients, so have the capacity to transform light in ways that other molecules can't. We've seen that organometallics can form components of efficient NLO switches, and that means that we can switch these properties on and off, and we can use this capacity for them to function as sensors as well. And one thing that I think that we've certainly recognised from our research and that everybody else that's been involved in similar collaborations will testify to is that international collaboration is imperative to advance science and promote international understanding. And we've certainly benefited greatly from our long-standing collaboration with various groups now at the University of Rennes. So I'd like to thank everybody at the University of Rennes for the collaborations, fruitful collaborations over many, many years. I'd like to once again thank the President Alice and the University of Rennes for the very great honour. And I hope to continue to visit Rennes each year for many years into the future. So thank you very much indeed. Thank you.
Merci Marc Humphrey.